So as a quick review of what we covered in past lectures, we're all about taking a function of time that's periodic and breaking it out into a sum, an infinite sum of cosines and of sines. So it's all of this. And every cosine is going to have a unique coefficient, and same for the sines. And they're all going to be, all the sines and the cosines are all going to be at integer multiples of your fundamental frequency. So if your f of t is periodic at omega naught, where omega naught is equal to 2 pi f, and f is equal to 1 over t, all that, then we can recreate it out of a sum of cosines and sines that are at integer multiples of frequency of the fundamental frequency of our f of t. And we can also represent this in a different format, where instead of using sines with no phase offset, we just use cosines, and this time we allow it to have a phase offset. And we call the top version, we can call this little a sub n's, little b sub n's. We can call it rectangular, and we can also call the bottom one capital A sub n's, capital phi sub n's, and we can also call this polar. The beauty of the top is that it's easy to compute. And I'll say easy, that's that integral where you multiply your f of t by either cosines to find your a sub n or by sines to find your b sub n's. The only way to find your a sub n's and phi sub n's is to construct this intermediate variable called c sub n, which is equal to a sub n minus j b sub n. And then your c sub n, your capital A sub n is your magnitude of your c sub n, and your angle is the angle of your c sub n. Now, if you were to think about this c sub n for a second, it's a complex number, and you can write that complex number in either rectangular notation here, which is why we call this version sometimes the rectangular version of the Fourier series, or you could write it as a magnitude and an angle. Which would be polar notation, which is why we call, so here's our polar notation, which is why we call this version with a sub n's and phi sub n's polar. So we have to start off calculating a sub n's and b sub n's, but once we do that, we can move it into this version. And now we could, if we wanted to, call this thing as a sum of phasors. So we could say it's equal to a DC value of phasor, and that's at omega equals 0, plus plus this phasor, which is at a omega of omega naught, plus this phasor, which is at 2 times omega naught, and continue that sum up on and on forever. And that second interpretation using phasors is what we're going to talk about today, because this is what's going to let us compute the output of any circuit to an input of any periodic function. And just as a quick review of where we're headed with that, when we began in circuits 2, we started off talking about sinusoidal state inputs, and those we handled using phasors. And then we talked about step inputs, and those we handled using bins at the beginning of the semester. We handled step inputs to a circuit, or things multiplied by a step. And what was our secret there to analyze them?
Says frequency.
Well, we did use the frequency domain, but how did you analyze a circuit? Maybe it had something like an e to the minus 2t u of t as an input to that circuit. What did you do to analyze that, Ben?
It would be Laplace transform.
That's it. Your first step was to find the Laplace transform of it, convert that over to an s plus 2 and analyze it there. And now we're going to talk about any periodic waveform at all, and that's going to be our Fourier series, which is going to be today's class. And that's pretty cool. It's a generalization of our sinusoidal steady state to work with anything. There is one last step with all this that we'll cover at the very end after this block, and that's going to be just anything. And for that, we're going to use a brand new thing called the Fourier transform, which we haven't yet seen. But this class is going to be talking about how to analyze an output of a circuit to any periodic waveform.